Hello and welcome to Physics Problems One by One.
So here is a problem. As always, read it, maybe once, maybe twice, and then pause the video and try to solve it yourself.
Today's problem is part 2 of the previous problem. The link is below in description. And it's again from Momentum playlist. Again, the link is there. But last time we discussed when the ball hits another ball and it's not head-on collision and they fly. This is V1 and this is V2 and they fly, and we prove that it is alpha plus beta equal 90 degrees, so they fly at 90 degrees. Today we try to do the same using simple fact that this is vector form of equation. So I will be dealing with vectors, not with the projections. And remember, I would advise you to read through pre-request vector playlist, but if you're confident that you know vectors, you will be able to understand right away. So let me draw this. This is initial impulse, initial momentum, and this is mv, right? And then this ball, that ball, it travels under this angle, and another ball travels under this angle, right? And so they travel in such a way that if I add this, this would be mv1. mv1, this ball, it will be deflected and it will be flying here and it will have momentum mv1 vector. And this ball that was at rest, this ball will start moving here and it will have this momentum in this direction. So this would be alpha and this would be beta and this would be one vector and this would be another vector. And because this is constant, I can write in vector form that this vector equals the sum of two other vectors. Vectors after the collision, when they flying at 90 degrees to each other, because we know that they're flying at 90 degrees. And I don't draw here a coordinate system. I simply say that this is one vector and this is another. And so I have to put this vector and put it to the end of this vector, and this would be my triangle. And so this, the length of this is mv2, the length of this is mv1, and the length of this is mv. Let me draw it again. This is a triangle, the length is mv, and it comes from initial momentum. This is another side of this triangle, and this comes from this vector, the first ball deflected, mv1, and then this is mv2, right? And m is the same everywhere, so I can cancel it out and it will be only like simpler for me. So if mass is the same at the same coefficient, it would be like this. So now I have a triangle. And let's put this angle, I don't know, gamma. It's my right to put this angle at gamma. And then I can write down the cosine law for this triangle, cosine law. And cosine law says that this side, v squared, it equals one side squared plus another side first. And it's already very familiar, right? Plus 2 v1 v2 cosine gamma, right? Everything is fine. And then I have to recall that because of the law of conservation of energy, mv squared 2 initial kinetic energy equal mv1 squared over 2 plus the kinetic energy after the collision. Remember, this is a full ideal elasticity, no loss of energy. And that's the only way that we can solve the problem if we add not only law of conversion of momentum, but also the law of conversion of energy. And again, m is gone, 2 is gone, it's everywhere. So we have that v squared equals this, so this would be gone, and we will have 2v1 v2 cosine gamma equals 0, and we have that this gamma equals 90 degrees. And that means that this triangle is rectangular triangle. And that means that this is 90 degrees, and this equals alpha plus beta, and we will have the same result, only we obtained it in a little bit more elegant form. And that's it. I think this solution is to a certain degree simpler, and it emphasizes that the law of conservation of momentum is a vector law. Because we dealt with the vector, we didn't even took the projection, no coordinate system. But yes, we took this law and law of conservation of energy. I hope you like it, I hope you subscribe, bell, and if you have questions, feel free to put it on in the comment section.